So this is a short historical survey of oceanography, at least oceanography as studied in the United States and Europe primarily, starting in about the 1700s. So the story of oceanography really begins with how sailors' logbooks, that is the books where they wrote down where they went and what winds and weather conditions they experienced and where they stopped and how to find places, how to get from place to place, so navigation. When those books were collected by each ship for the purposes of keeping track where they had been and keeping track of trade routes. But in the late 1700s and through the 1800s, those books started to be used in a more scientific way. One early example was Benjamin Franklin, and quite a few others followed up on that in the scientific use of the logbooks. And then the other thing that was a key discovery in around this time was the Harrison clock. And that was a way to tell time even when you were at sea, which allowed you to get a precise longitude. We'll talk a little bit more about that as we go along. So here's Ben Franklin, and here's Ben Franklin's map of the Gulf Stream. The Gulf Stream is the largest current in the Atlantic Ocean. It's one of the largest currents in the world. And Franklin discovered it because he had gone back and forth between the United States and France a number of times, and he realized that when they went one direction, they would go faster than when they went the other direction. He talked to the captains about it, and they said, well, there's this big river in the sea that carries the water, and if you ride on that, you can go faster. And so Franklin discussed this with a bunch of different captains, analyzed their logbooks, and made this map of the Gulf Stream. Captain Cook, James Cook, was another one of the great explorers, but unlike the explorers who were looking for only trade routes, a lot of Cook's missions had a scientific agenda as well. And so this is the 3 different voyages of Captain Cook and his crew as they went around the world. And the amazing parts of their journey are these long transects in longitude where they're going from east to west, far out of sight of land, without any real landmarks or anything that they knew. So circumnavigating Antarctica, this is sort of an extraordinary thing to do, and it was really enabled by the fact that you had this clock. So here's Harrison, and here's the clock that Harrison made, or one example of the clock up here. And so the problem with clocks before Harrison's clock was that clocks were pendulum clocks that you would have in your house. But of course, if you're at sea and the ship is bouncing around, you can't use a pendulum clock. So the Harrison clock is based on springs, and so it functioned at sea. So why do you need to know what time it is? Well, you can use the North Star or other constellations to figure out what latitude you're at by measuring its height above the horizon, but you can't figure out what longitude you're at unless you know what time it is. Effectively, you need to know what your time zone is, or what the reference time is in a city whose longitude you know, and then you compare that to your local noon. And that way you can figure out what longitude you're at, because you can figure out where the sun is in the sky at different times of day, or moon is in the sky as well. So this little summary of what was going on from a description is talks about this clock never exceeded 8 seconds off of true over an entire voyage. So that's pretty astonishing over these multi-year journeys. All right, so now we know that science is interesting. We know that we can help in trade and navigation by having better science. So throughout the 1800s, science just got more and more exciting in the ocean because now you knew where you were, and so there was a burst of the development of different kinds of instruments. We're going to talk about some of them. And Antarctica was discovered as well. And the evolution, the theory of evolution or the natural selection really came from comparative biology on these kind of missions as well, which we'll talk about. So here is Maury, and Maury was an important figure in oceanography or sailing directions in the mid-1800s. First for the US Navy and then for the Confederate Navy. Maury compiled ships' records and made depth charts from their soundings, which at the time was lowering weights down to the bottom on a rope and bringing them back up, and from that you could make charts and you could make global wind and current patterns. And so here's an example of mapping the northeast trade winds and the southeast trade winds, the latitude range that they occur at, and then the number of observations. You can see that this is in the tens of thousands that give you these records. And here's Darwin as a young man. So Darwin went on the Beagle, and this is the voyage of the Beagle going around like this, around the Earth. And as we all know, Darwin discovered by comparing, and particularly spending a lot of time in the Galapagos Islands over here, tried to understand why species were so different in different locations as they went around, particularly in islands where there were species that were similar to, but not quite the same as the mainland version of the same species, finches and such. As we mentioned in class the other day, he also wrote a book about the way that tropical islands grow and how coral and the geology interact with one another. This was such exciting science that even science fiction started to be written about this exploration and exploration under the sea. So maybe the most famous example of this is Jules Verne's 20,000 Leagues Under the Sea, which is just a fun book about a lot of topics about the cutting edge of mid-1800s science. Right around this time, the Challenger, another British expedition after the Beagle, went around, and this was notable because it didn't have any trade or military agenda. It was a purely scientific expedition. They did a lot of deep trawls and found lots of strange critters in the deep sea. Some of the pictures of those are up on the right-hand side. They also mapped temperature and salinity, and from that, they were able to make large-scale analysis of what the temperature and salinity structure of the oceans were like on the paths that they followed. They also examined sediments from different locations. So the Challenger is still another of these kind of major scientific explorations. The Challenger invented the idea that there was a climatological structure of the ocean that one could go out and measure, that it was the steady, persistent structure of how temperature and salinity would vary throughout the world. And all you had to do was go out and measure it once, and then you would know. Kind of like mapping the Earth. So another of these classic journeys was the Fram, which means the forward. And here's the Fram frozen in the Arctic ice. It was a specially reinforced hull so that when the ice froze around it, it wouldn't be crushed. And so this crew, led by Nansen, here he is as a young man, about the age he was when he went on the Fram, and here he is as an older man, around the age he was when he won the Nobel Peace Prize for helping prevent starvation after World War I. But anyway, the Fram crew froze themselves into the ice, They did a lot of science. They wrote a really fascinating set of books about what they observed and the tides and the winds. And, you know, the idea was that they were going to try and get to the North Pole by drifting along with the pack ice. Rather than being under power, they were just going to do it on their own. After a while, though, from charting their location, they started to notice that they weren't going to get that close to the North Pole. At which point, their provisions started to get slim, and in particular, they ran out of beer. And shortly after this occurred, Nansen decided that he needed to ski for the North Pole. So he and the mechanic put on cross-country skis and started skiing across the pack ice for the North Pole, leaving behind the rest of the crew to get home on the ship. The crew did eventually break out of the ice and get home on the ship. And then Nansen and the mechanic got close, the farthest north, as they called it. That's the title of Nansen's book, Farthest North. But they didn't quite make it to the pole. But amazingly, after skiing across the polar ice for months, they ran into the only other scientific expedition that was anywhere nearby and got a ride home. And in fact, they made it home, if I'm remembering correctly, they got home before the rest of their crew did. So what kinds of instruments were people using? Nansen invented this one. He wasn't only an explorer, he was also an inventor. And this is called the Nansen bottle. And it's similar to the reversing thermometer. The idea is that it's attached at the top and the bottom like this, but the top attachment has a release. So you would drop a little thing, a little brass weight called a messenger, and the messenger would come down, it would hit this clip, the clip would release, and the bottle would spin over and then clip back in at the bottom. And when it did, it would release another messenger from the bottom to go down and release the next bottle in line. So you could drop a messenger from the top and hear them go ping, 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 as it was going down and releasing bottle after bottle all the way the length of this cable that you would lower down as deep as you could go. In this reversing process, the openings at the ends of the bottle that had been filling with water would seal shut as part of the rotation of the bottle. So you would get a sealed sample of the water from the depth that this bottle was suspended at when the messenger hit it. And when you pulled it up, since the seals had closed up, it wouldn't be contaminated by the water as it was being pulled on the way back up. So this is a very clever piece of engineering. At the same time, you would frequently mount reversing thermometers. So a reversing thermometer is like this. It's a regular mercury thermometer, but it's such that if you tip it over, the amount of mercury, that is the temperature, would pool on the other end and be stored so that when it flips over, you wouldn't gain any more mercury or lose any more mercury if the temperature changes as you returned it back to the ship at the surface. And so what that means is you could record the temperature when you flipped the bottle when it hit with the messenger. And even cooler, one of the bulbs would be protected from the local pressure. It would be in a pressure housing, and one would not. So the difference in temperatures, or the difference in mercury pressures that you read between these two side-by-side thermometers would actually tell you what pressure the instrument was at. And since pressure increases with depth in the ocean, you could measure simultaneously, together with a Nansen bottle and a reversing thermometer, temperature, salinity, or water type, and pressure. If you could sample water and get the temperature and the pressure, you were able to map what was going on underneath the boat. It's still a slow process because you have to lower that cable down maybe many kilometers and then send those messengers. If the messengers didn't accurately release the bottles, you have to pull the whole thing up and start over again, etc. But it's a pretty ingenious way of sampling the ocean. So Nansen was one example, but the Scandinavians actually were heavily involved in both seafaring and trade, and also they, in the early 1900s to mid 1900s, a series of Scandinavian oceanographers and atmospheric scientists took the fundamental fluid mechanics theories that had come from Laplace and Newton and Euler and Lagrange and Stokes before, in the 1800s, had written down equations of motion for fluids that they had studied in the lab, but the Scandinavians were the ones who really figured out how those equations of motion related to the kinds of things that they were observing. Different kinds of water, interfaces between lighter water at the surface and deeper water that causes a phenomenon called dead water that we'll talk about, and importantly, the Ekman spiral, which we're going to spend a lot of time talking about when we get to winds driving the ocean. This continued well into the mid of the 20th century, and even at present, Scandinavian dynamical studies of the ocean and atmosphere are important. Another important expedition in the early 20th century was the Meteor expedition. And one of the big advances that they had was they actually had sonar. So they were able to map the seafloor underway. And so they put this together with, this is a nice current meter that you can see there's a little propeller that spins and could be recorded what the rate of rotation was. So you could measure the currents at different depths. They measured different water masses that had different properties of temperature and salinity, and the rugged seafloor underneath. Here's an example from the atlas of the Meteor expedition. They went back and forth and back and forth and back and forth and back and forth across the South Atlantic like this. Here are some of the temperatures that they measured as they went, and you can see that there are subtle changes in temperature from one side of the basin to the other. And then here are anomalies in temperature where there's kind of a blob in the middle, colder above and below. You would think that that might be unstable, that this water would be lighter than what's above it, but if it's also saltier, it could be warmer and saltier below. Not only was the Meteor doing science, but the Meteor was also a demonstration of military might. The idea that you could conquer such a large part of the oceans and sample from it was definitely part of the story as to why these expeditions took place. And here's more images from the atlas of the Meteor, mapping the salinity anomaly that comes out of the Mediterranean, like this, and then temperature structures along with it. And these are as depicted by WOCE in the 70s, but based on these observations of the Meteor in the 1930s. The Atlantis, the famous first of the Woods Hole Oceanographic Institution vessels, which is a sailboat, sailed all over the Atlantic in the neighborhood of Woods Hole, which is close to where we are over here. And you can see some of its tracks as it went around. And as we're getting into the 50s and 60s, there was an international geophysical year, which now, instead of having one country try to dominate an entire section of the world and demonstrate its might, this was an international collaborative project. This is now the post-war era. And so the United States and European countries got together and did this entire mapping of the Atlantic. And, you know, as they thought at the time, everything was stable and stationary, so that would be enough to do it once and for all. And here are some examples of the atlas of that. And this is now mapping these different water masses. So a water mass is a mass of water that has a particular temperature and salinity profile. And normally we think of it as getting set or formed at the water surface. So this, the Antarctic intermediate water, is formed here in the Antarctic circumpolar current on the north side of that current. And that water comes down, moves this way, and it has a recognizable temperature and salinity anomaly. A little bit deeper, the water is coming the other way from the North Atlantic deep water. I should say this is an Atlantic profile. And the lower panel is in potential temperature in the salinity in the lower panel, potential temperature in the upper panel. So you can see that the potential temperature, and what potential means we'll talk about soon, but temperature essentially is warm at the top and cold at the bottom, with some exceptions. And those exceptions are in the same location as where the salinity exceptions are. So if I was to show you density, density would be uniformly increasing towards the bottom, but it's partly from the colder and partly from the saltier that the density increases. So here's the North Atlantic deep water that comes down this way and forms up here in the North Atlantic. And then here's the Antarctic bottom water, which is the most common water type in the entire world. And it's formed right near Antarctica and the Ross and Weddell Seas. And it is the densest water in the world. It fills up the bottom of the ocean. So oceanographers call bottom water a water that sits on the bottom, deep water, a water that's deep, typically between 1 to 2 kilometers of depth. And here you can see 1 to 3 kilometers of depth is what we're looking at for the North Atlantic deep water. And then intermediate water is in between the deep water and the surface waters. And surface waters have a variety of different names. So how long does it take for that Antarctic bottom water and deep water to get down there? Well, it's kind of hard to tell, but some clever folks like Jeff Gebbe and Peter Hoybers have been able to estimate the age of those water masses by using radiocarbon dating, which this is a complicated aspect of things that we're not going to go into too much detail on, but this is basically a map of the Pacific, the Indian, and the Atlantic Ocean, and their age in years from 0, that is just formed at the surface, so all the surface waters are at 0, up to 1,500 years old in the deep Pacific. Those overturning circulations that we just saw in the Atlantic keep it relatively young, so that the Atlantic waters are between 500 years and 0, pretty much, except for maybe the bottom part of this deepest Antarctic bottom water. But in the Pacific, where there's no deep overturning in the northern end, and the Indian, where there's similarly no deep overturning, the water below gets really quite old. So that's thousands to 1,500-year-old water. Oh, and I should say age, I mean age since it was last at the surface. Okay, so what about the bottom of the ocean? Well, we talked about the meteor going around and pinging off the bottom with sonar. Once you get enough of those maps, you start to get a sense of the topography of the bottom. So Mary Tharp and Bruce Heezen and Lamont Doherty in the 50s through the 70s made maps where they were using the available observations and then using their sense of geophysics to link the kinds of ridge systems that you would imagine that would have to arise in between the observed locations. So they made complete detailed ocean floor maps of the whole world by inferring the structures in between the known locations of things like seamounts, like these are here. Some decades in the 20th century actually didn't have a whole lot of observations. This is all of the high quality observations in the world between 67 and 78. Not a whole lot going on. One of the things though that did happen soon after this was that they figured out that actually the oceans are not so steady. They started to observe these eddying features. We'll talk a lot about this. I'll show a couple movies at the end of this video. But there's still not too much data, even as we go into the 80s. So from the 80s to 2000, there was a coordinated world experiment. Now, all of the countries in the world that have oceanographic vessels collaborated on this world ocean circulation experiment. The Seidler volume that we use for this class is actually the second edition of an atlas or a discussion of all the things that they'd learned from this. So lots of great stuff happened. So they set out to measure all the time and space scales over the entire world. So they knew that there was variability by now. They tried to get small spatial scales as well as large ones. They went for global coverage, and they did repeat sections because they were interested in detecting trends. They use moorings, they use drifters, they use ships, they use satellites, and they use numerical models, all as part of the WOCE experiment. So here is the map of all the transects that the WOCE experiment did at least once. You can see that there's a whole lot more in parts of the world that were previously not drawn on those maps, like the South Pacific and South Indian Ocean. And that led to a lot of really great context for what the whole temperature and salinity structure of the ocean looks like. All of this data is available to you for the class if you wanted to look at one of these, and a lot of these sections are actually repeat sections. So they go back at varying times depending on which section it is. So you can look at both the original data, but also how the data is changing over time in some of these sections. But one of the other things that came along with WOCE was the idea of using autonomous floats together with a GPS tracking system. So these floats change their buoyancy, and they basically go up and down from about 2,000 meters depth up to the surface, call home on a cell phone network, registering their location with a GPS sensor, and then drop back down to 2,000 meters drift for a week or 10 days, pop up and down, measure temperature and salinity the whole way as they go. So this is just a density map showing all the observations within a given 5-year window. So relatively sparse here in the 50s, pretty sparse in the 60s, 70s, 80s, so on and so forth. And then look, wow, there's a lot of stuff going on here in WOCE. You can see the WOCE lines appearing, but then when this autonomous system kicks in about 2003, you see that the global profiles of temperature and salinity suddenly starts to actually cover the whole world. This was in this Argo project is one of its key targets is to measure the changes in ocean heat content. That is, how much the temperature and salinity structure of the ocean are changing and with respect to climate change. And that's just a different visualization of them. But still below where they can go, these 2 kilometer depth that the Argo floats go to, those profiles are still quite rare. There are a few select deep profiles, and you can try and make a map like this map by Perkey and Johnson, and try and estimate whether those different deep water masses are changing. Maybe they are changing because of global warming, or maybe they're changing because of the changes in climate on multi-centennial scales. As we just saw, some of these deepest water masses are 1,000 or 1,500 years old. So you wouldn't expect them necessarily to be responding yet to climate change. And here's one of the coolest papers to talk about a historical perspective on oceanography. This paper by Dean Remick and others took one of the Challenger expedition, one of the expeditions we talked about, and compared it to Argo profiles in the same locations. 135 years later. And this is the key figure over here. Well, both of these figures are key figures. These show how different the temperature is between the modern Argo profiles and those Challenger profiles. And you can see that a lot of them are a lot warmer. Here's an average of different profiles that were compared over the upper ocean. The Argo profiles tend to be about 0.4 degrees C for warmer over something like the first kilometer of depth. That's a clear signature of climate change in this record, or the difference between these two records. You can also wonder about whether the Nile is changing is another indication of climate change, indicating changes in precipitation. Whether the Florida current, the Gulf Stream is changing. This is an interesting place to measure because you actually can use telephone cables to go underneath the seawater. Because the seawater has charged particles in it, it induces a current in the telephone cables as it goes over the cable. Henry Stommel, one of the scientists we'll talk a lot about, was able to reconstruct this time series based on this method, and it goes all the way back to when that seafloor cable was installed. So a pretty substantial record with a lot of high frequency variability. Maybe no long-term trend, but a lot of variability was captured by this method. On land, of course, you have even longer temperature records. This is a temperature record, one of the longest or I think the longest temperature record, daily temperature record, going back to the late 1700s. And you can see that it's warmer on one end than it was at the beginning. Along with the variability due to eddies, the surface layer, or the mixed layer, the well-mixed layer of the surface, changes its temperature with the seasons. This is one location in the mid-Pacific called Ocean Weather Station Papa, or actually now it's called Ocean Climate Station Papa, and it's a mooring that's permanently installed at that location, and it has sensors on its mooring cable that measure temperature and salinity as it goes down. So it shows that as we go through the season, so January, April, August, October, December, January, there's a cycle of changes of temperature at the surface and changes of also the mixed layer depth, how deep the well mixed layer is before you get to the deeper stratification. So January and December have very deep mixed layers. October and August have very shallow mixed layers, warmer, shallower mixed layers, and April is a transition zone between the shallower and the deeper. You might ask why it only goes about 60 meters deep here, this effect. Doesn't the atmosphere change a lot, its temperature? Well, actually, the atmosphere doesn't have a whole lot of heat capacity. That is, it doesn't take a lot of energy to heat or cool the atmosphere. Air is easier per unit mass to heat than water is, but also the ocean is a lot more massive per unit meter, per meter than the air is. So the atmosphere is much more sensitive to changes in energy than the ocean is. So something like a 1.5 degree Kelvin change per year in the atmosphere, which is equivalent to 0.7 watts per meter squared of warming, which is about the magnitude of global warming, would lead to a 1.5 degree Kelvin per year change in the atmosphere, or a 1.5 Kelvin change per year in only the upper 3.4 meters of the ocean, or the upper 34 meters of the ocean would be a 0.15 Kelvin per year change, which is about 1% of this seasonality. So the point here is global warming is only about 1% of the natural variability in the upper ocean temperature and that annual cycle. So it's global warming is a small perturbation on a very large seasonal cycle of exchange of energy between the atmosphere and the ocean. And the upper 3.4 meters of the ocean has the same heat capacity as the whole atmosphere. But this mixed layer might have 10 times as much heat capacity as the entire atmosphere. So when we think of the atmosphere and mixed layer system together, most of the energy is actually residing, most of the energy variability is actually residing in the ocean, not in the atmosphere. And that's consistent with how much of the anomalous warming in the Earth system happens in different places. So here's what, if we take the global warming signal, about the 90% of the anomalous warming occurs in the oceans. So here's a bar chart showing that most of it occurs in the ocean. This is a little bit more accurate, more updated, recent Argo-based energy budget. And you can see that from this one to this one, they're consistent, at least over these different decades, in terms of the error bars overlapping, but they're also the non-ocean parts of the Earth system that are warming are actually really tiny contributors to this story. And there are a lot of challenges in studying the ocean. One of the most difficult, of course, is that unlike the atmosphere, you can't see through the ocean. So you can't study like the formation of clouds and the motion of storms that way. You have to use acoustic techniques or all these remote sensing techniques, like in situ sensing techniques. It's hard to get to most of the ocean. You'll be crushed by the pressure. So they're submarines, they're big ships, they're all very expensive to operate. The ocean pressure increases by an atmosphere every 10 meters of ocean depth. The oceans are extremely deep. It's really hard to carry around long, 4-kilometer long wires. This makes it difficult to study the ocean. And seawater is also enormously corrosive, which makes all of your electronics go haywire while you're out there. And there's a whole lot of waves and foul weather conditions, typically in the places that are the oceanography is the most interesting, where the big air-sea exchanges occur is where all the waves and weather are really, really dangerous for being out there in a ship. The modern version of the Nansen bottle is something called the CTD, together with a Niskin bottle rosette. So a Niskin bottle is a lot like a Nansen bottle. It's open on both ends, and then you can trigger it to seal shut. It doesn't flip over. It just has electronic and kind of bungee corded caps that pop into place when you release it with an electrical signal. And then in the middle on this little guy, there is the conductivity, temperature, and depth, which is like the modern version of the reversing thermometer. It gets depth from the pressure, it gets temperature from the a thermocouple, and it gets conductivity, which can be converted into salinity if you know the temperature and the pressure. So this measures salinity, temperature, and pressure. And that is enough to make profiles of those as you lower an instrument like this through the water. And since it's an electronic measurement that's continuously measuring, you actually can see very small scale wiggles in things like salinity and temperature. This is one of the earliest measurements of that. Small scale wiggles are now known as fine structure. The fine structure is indicative of very small turbulence and interleaving waves and layers. And once you get the idea that there might be fine structure in the vertical, you might actually start towing a CTD horizontally. And when you do that, you find that there are horizontal variations in the temperature and salinity on relatively small scales. So here are these little fronts, and frontlets, which lots of folks in my group study. Those fronts might only be a few hundred meters wide or even tens of meters wide, and have pretty substantial density changes. So as we go here in the mixed layer, the surface part of the ocean above the stratification below, this is showing temperature, or sorry, this is showing density, sorry. So here's the mixed layer, which is well mixed in density in the vertical. It's actually not so well mixed in the horizontal. There are pretty substantial density jumps that have to do with surface features called fronts. Another instrument that was kind of a big part of the exploration pre-Argo was the expendable bathythermograph. And here's the gun, and here's the bathythermograph itself. It looks kind of like a little spaceship. You would fire one out of this tube into the water, and a spool of wire would unspool as that weight would sink. The weight is measuring the temperature on it, thermograph. And so the thermo part is measuring temperature. It's going deeper and deeper and deeper. And then at a certain point, it gets too deep and the wire breaks. But because you have contacts to that wire the whole time, you are actually able to electrically record the temperature as it went down from depth to depth. These are still used now. A modern version of these is still used. The advantage, and you can even fire them out of aircraft now. The advantage is that they're quick. The disadvantage is that you don't get the instrument back. So you have to buy an instrument for every measurement you take. And lastly, GPS is a big advance. It's a satellite navigation-based system. So a little device like this can tell you exactly where you are, or well, within a few tens of meters of where you are, which is a whole lot easier to do than this complicated thing of using a sextant like this to find the angle of the sun above the horizon and using this fancy Harrison clock to figure out what your longitude and latitude were. From satellites, you can measure a lot about the ocean surface, like its color, which tells you about the temperature and chlorophyll, and actually salinity to some extent as well. The rainfall you can measure from space, wind scatter, that is the small waves that indicate the presence of wind. You can measure big waves as well. You can measure the geoid. You can measure the mass through gravity satellites. So all of these different measurements give us a picture of what's going on at the surface. Unfortunately, because almost all of them are electromagnetic measurements, they don't penetrate very far through the surface because light doesn't go through seawater very well. The one exception are the gravity satellites, because gravity does penetrate through the ocean. So you actually get a mass of the ocean, of the whole depth of the ocean from the surface to the bottom using a gravitational satellite. And so if you know the ocean mass from this gravitational satellite, this one is called GRACE, the Gravity Recovery and Climate Experiment. And then you know the sea surface height from measuring the height. How did you measure the height? Well, you can ping either a laser or a radar against the surface and measure how long it takes to go down and then back to the spacecraft. Amazingly, even though these spacecraft are at hundreds of kilometers above the surface of the Earth, they can measure that ping with a measurement accuracy on the order of centimeters. So they're measuring a centimeter hundreds of kilometers away. But if you can do that, which we can, you can measure the height of the ocean surface, and we'll see that the height of the ocean surface is a critical variable for dynamics of the ocean, but it's also a critical variable for sea surface height. So sea surface height is a big part of climate change. As oceans warm, they expand. And as they expand, they tend to flood coastal cities. And so people don't want that to happen. They want to understand how that's going on. So you can measure the sea surface height directly with an altimeter. That's what this blue one is indicating here, and the range is uncertainty. Or you can figure out what the sea surface height should be if you know the ocean's mass from the gravity satellite, and you know the ocean's temperature and salinity, and therefore density from the Argo project with those drifters, you can put the mass and the density together. So sea level is the ocean mass divided by the density divided by the area. You get an estimate of what the sea surface height should be. That's this dashed line. And the fact that this dashed line lies on top of this altimeter means that this story is closed. By observing the gravity part of the ocean and the thermal part of the ocean, we can get the sea surface height, and we can get it in agreement with the sea surface height directly measured. So that means that there's nothing missing. We're not missing any other expansions of seawater or any extra mass of seawater that's coming from any other source. You might wonder why we have to measure the mass. Isn't the ocean mass fixed? Well, it's actually not fixed because of things like the melting of ice sheets and the melting of glaciers and the changes in size of, say, ponds and lakes and rivers on land as the precipitation changes. So the ocean mass actually comes and goes with all of those changes on land and in the cryosphere. This is just another example of things we can measure from space: high resolution wind stresses. And so we still need the in situ measurements for the deep measurements. So we talked about Argo, but there's also a mooring array all around the tropical world. And it's just a map of them. They have things like instruments below the surface, as we might imagine, but some of them also have meteorological buoys on the top to get winds and things like the amount of radiation coming from the sun. You can measure not only the bottom using sonar, but actually you can ping a sensitive sonar against the motion of particles in the water. And if they're moving toward the instrument, that'll be detectable. If they're moving away from the instrument, that'll be detectable. If you use multiple beams like this, you can actually measure the velocity, all three components of velocity, by comparing the scatter you get from different directions. This is called an acoustic Doppler current profiler. And they mount these on ships. They put them on moorings. They put them on the bottom of the water. This is a great instrument for getting a profile of velocities. And sonar we've already talked about, but sonar now is not just a single beam. They actually use a scanning sonar that goes side to side. And so you can make maps of things like this wreck or canyons. It's a really amazing process. And then, of course, we've already talked about the automated floats. But here's a picture of how they work. They spend about a day at the surface. They drift to depth. They come up. And when they're going up and down, they're measuring the temperature and salinity. And the amazing thing is just how many of these you can afford. They're not very expensive instruments. And so there are about 4,000 of them in use all the time now, all around the world. And they it doesn't require an expert to launch them. So they are launched from just ships that are going in places where they happen to be sparse. They hand them over to the crew of the ship and just say, just drop it overboard at such and such a time and off, or such and such a location. And that's enough. And those microstructure probes, the fine structure we saw, this is an even more accurate thing called a microstructure probe, and it has very sensitive conductivity and temperature sensors on it, and it can measure the amount of turbulence at very small scales in the ocean. And so a probe like this would be dropped and it would lower itself down and measure turbulence. And this is an example of how turbulence varies over bumps on the bottom of the ocean in the Scotia Ridge. I think the last instrument we're going to talk about is the rapid system, which is monitoring the overturning circulation. So those water masses, the North Atlantic deep water, sinks down and is replenished at the surface. There's actually a series of moorings across the North Atlantic at 26.5 north, and it measures that meridional overturning circulation, the Atlantic meridional overturning circulation, which is that North Atlantic deep water on one side and that surface water on the other. And then here is the and these different lines are showing the Gulf Stream contribution, the surface wind drum contribution and the upper mid-ocean contribution, leading up to this net overturning of about 20 spheredrups. And a spheredrup is 1,000,000 cubic meters a second, or 1,000,000,000 kilograms a second. That is a whole lot of water that's moving and overturning to supply that North Atlantic deep water. There are now 2 other monitoring systems built on the same principle as RAPID, one called OSNAP, which is farther north, and one called SAMOC, which is in the southern Atlantic meridional overturning circulation. All right, so we've got all of this data from all these different data types, and I hope you've gotten a sense of it from my talk. You can see that WONCH goes through pretty much the same story on pretty much the same kinds of instruments. What do we do with all this stuff? We've got data, we've got data, we've got data. One thing we can do with it, and the approach that we're going to use most often in this class, is you take all that data and you put it together into a model, and that model tells you what the fluid is doing in a way that is consistent both with the laws of fluid motion and with the observations you have. So it puts together the laws and the observations, and it makes a version of the ocean, a version of the ocean state. It is an estimate of the state of the ocean, a state estimate that is most consistent between the observations and the physical principles together. And since there is uncertainty in the observations, and there is unsampled regions in the observations, and there is uncertainty in the physical modeling as well, because the resolution of that model doesn't capture all of the features that it could possibly capture. The small scale things are left out. Both are a little bit approximate. And so what data assimilation does is it puts those 2 together and tries to optimize in the face of that uncertainty. That's what the appendix of the WONCH book will tell you about. And we'll be using the ECHO model, which is estimating the current climate of the ocean. And it's actually a state estimate, which WONCH, the author of the book, was heavily involved in developing. So when we think about the big picture, we go from Franklin's Gulf Stream to this much more complex vision of the world in terms of the gyres and circulations in the horizontal, like this. So the things that are looping around the vertical axis look a little bit like this. They all have names on them. And here are the meridional overturning circulations. Here's the Atlantic one with the North Atlantic deep water. Here's the Pacific one with no deep water formation in the North Pacific, but the Antarctic bottom water coming and coming back up. And there's a similar circulation in the Indian. And then there are these funny places like the Indonesian through flow, where the Pacific is linked to the Indian Ocean, or Bering Strait, where the Pacific is linked to the Arctic, which is linked back in through the North Atlantic, coming this way. And I'm going to switch over now and show you some variability. So if we make a movie of the surface currents of the ocean from altimeters, you see that the whole world is not a steady picture of steady temperature and salinity and currents, but instead it's something that's moving like crazy. These are mesoscale eddies. These are large scale currents. You can see the Gulf Stream here is wiggling and moving. Here's the Kuroshio. Here is the tropics, which are dynamic and constant wave motion and activity. Here's the Antarctic circumpolar current. And there's just so much to look at in this. Notice also that how quickly the time is clicking by here. This is made from an altimeter. And what we're looking at here is the logarithm base 10 of the kinetic energy. the U velocity, east-west velocity, plus the north-south velocity squared. 1/2 of that is the kinetic energy. So this is the base 10 logarithm. And you can see that it spans 1, 2, 3, 4, 5 orders of magnitude. So these places are 5 orders of magnitude. So that is not 1,000 times, not 10,000 times, but 100,000 times less energy than the places that are dark red. Let's see. Here's another example of things we can see from satellites. Here's Hurricane Katrina forming, which you can see in the clouds. When Hurricane Katrina goes by, it mixes up the ocean and brings up cold water into the surface. So the colors here are showing sea surface temperature, which were detected by satellite together with those clouds. Here's an example of what an ocean model looks like on the global scale. Now we're looking at velocity, not kinetic energy. Sorry, this is not velocity, it's speed. And so you can see these dark spots where there's just no detectable speed, but there would have been if we'd used the logarithmic scale like we did before. But there are these parts of the world that are not only highly energetic, but highly wiggly. This is a version of the ECHO model that is similar to the one we're going to be looking at. It's actually a higher resolution version, but this is similar to what we're looking at. And you can also see the growth and shrinkage of sea ice in each of the hemispheres as the winter time comes on, and snow on land. So I think you are definitely convinced now that the ocean is a vast and diverse place. And there's all this stuff going on. But when we use a climate model or an ocean model or one of those or a state estimate, it's only going to resolve a narrow band of that whole diversity of stuff. So we need to go out and observe, and that's the way it's going to be for a long time. Thanks very much. If you've enjoyed it, this is a quick tour of the history of oceanography from the 1700s to the present.